Hi, everyone. Good morning. Thank you for attending the last session of this workshop. And for the first talk, we're very excited to have Kaavya Sahay, who is a grad student in Shruti Puri's group in Yale. She's working on quantum error correction theory. Her talk will be about designing high threshold error correction protocols for qubits that experience biased erasure errors. And I'll give the floor to Kevin.
Okay, thank you for the introduction. My name is Kaavya. I am a student in Shruti Puri's group, as Murphy said. Today, I'll be talking about work that we put up on the archive a few months ago. This was a theoretical proposal that was born out of a collaboration between neutral atom experts at Princeton and a theory team at Yale. In this work, we explore how to build error correction protocols with high error tolerance thresholds when our qubits experience a form of error known as biased erasure, thanks to our collaborators and the support of the NSF. So there are a few messages I'd like you to take home from this talk, and they start off with this first one, that there exists a form of structured noise called biased erasures that has as yet been unexplored. And this biased erasure error model is in fact the dominant error in the metastable ytterbium-171 neutral atom qubit. And when we analyze this error model using an error correction code called the XZX surface code, we see high error thresholds. Specifically, we see a gate level error threshold of 8.2%. This is about 8 times the error threshold for regular depolarizing poly noise, and about double the threshold for conventional unbiased erasures that had been studied till date. Why this is such a remarkable result is that if you have gates in your experimental protocol that experience an infidelity of 5% or only succeed 95% of the time without errors, you are not in the error correctable regime. If these errors are poly errors or conventional erasures, you cannot achieve fault tolerance. However, if your errors are in fact biased erasures, you can in principle still achieve fault tolerance with these faulty gates. We then looked more closely at our error correction codes and the capabilities of the qubits themselves, and designed a new measurement-based protocol that we called hybrid fusion that was designed to relax the hardware requirements in order to achieve fault tolerance. And as a byproduct of this code design, we increased the threshold to 10.3%, along with reducing the qubit overhead and decreasing the requirements for atom replacement rates. So all of these nice results seem to stem from this error model, which is called biased erasure. And I'll now talk about how this manifests for the neutral atomic qubit. Our qubit itself is encoded in this 6s6p 3p0 level of the ytterbium atom. And how we perform gates on this qubit is we excite the one state to the Rydberg level and have it interact with another atom that is similarly excited to the Rydberg state. This gives the 1-1 state a phase and enacts a control Z gate on our 2 qubits. The dominant error mechanism during this process is decays from the Rydberg state to a set of external states that we can call E. And what we can do is we can place a fluorescence pulse that detects populations in this external state E. And in fact, this is the definition of a conventional erasure, a heralded leakage from the computational subspace to an external state that we know has happened. But if we look more closely at what is happening during this process, we see in fact that it is only the one state that is excited to R and then decays to E. So in fact, we have a slightly different error model. Instead of erasure, where leakage can occur from 0 or 1, we have a biased erasure, where this heralded leakage that you can detect only occurs from the one state. Now, once this biased erasure occurs, in our protocol, we replace the qubit with a fresh atom in the one state. Now, this fresh atom is in the correct computational state, the one state that our original qubit was, but it has lost all phase information associated with the original qubit. And as a result, we can introduce at most Z errors to the effective qubit at that location, as shown. So now we're going to study qubits that experience this error model in two contexts. The first context being the gate-based error correction protocol called the XZX surface code. We're then going to move on to study the hybrid fusion protocol, which is a measurement-based approach. So starting out, I'm going to perform a brief recap of the XZX surface code. So the XZX surface code encodes a single logical qubit in a lattice of physical qubits, where here the physical qubits are present at each vertex of the lattice, and each face or plaquette represents a stabilizer operator, where we measure the operator X, Z, Z, X, using a series of 4 gates. So we initialize our ancilla in the plus state, perform a control naught to control Z's and a control naught, and then measure out ancilla in the X spaces. We do this for all the faces on our surface code and recover the stabilizer outcomes. If there are no errors, our stabilizers should all return +1. There are only a few ways that we can flip the state of this logical qubit given errors on the underlying physical qubits. One of them is if we have a string of X errors on the underlying physical qubits that stretches vertically across the lattice. The second is if we have a string of Z errors on the physical qubit stretching horizontally across the lattice. This performs a Z poly on the encoded logical qubit. As a result, if errors on the underlying physical qubits can give rise to errors on the logical qubit, it's important to study what the stabilizer outcomes under certain patterns of errors look like. So let's examine an error on the central qubit. If we have an X error, the stabilizers to its left and right commute with that X error because they have an X operator on that central qubit. However, the stabilizers above and below it have a Z operator on that central qubit. And so when you measure the stabilizers, you see -1 outcomes, which we call syndromes or defects. Similarly, if you have a Z error on that central qubit, what you have is stabilizers above and below it that commute with that error, but the stabilizers to its left and right anti-commute and produce syndromes or defects. Now, while doing error correction, we do not have access to the underlying physical qubit state. We can only see these -1 stabilizer outcomes. And our job is to look at these -1 outcomes and locate and correct the errors on the underlying physical qubit. For this simple case, it's easy enough. We can pair these two defects together and apply Z corrections to the qubits that lie on the path between them. And we know that we have to apply a Z correction because here it is a horizontal path between these two defects. So this brings us to a nice subtlety of the XZX surface code, which is that if your qubits experience naturally a biased noise model, which is to say that your rate of poly Z errors is much, much higher than your rate of X or Y errors, then the XZX surface code behaves kind of like a repetition code. What do I mean by that? If you only have Z errors, then you only have pairs of defects produced in horizontal directions. You have no error that will produce a pair of defects in the vertical direction. And therefore, you can treat each horizontal line in your surface code separately, which looks effectively like a repetition code, and pair defects along these horizontal directions. This reduced dimensionality of the pairing or matching problem is what we colloquially call asymmetry in our surface code. And in the limit of infinite bias with only Z errors, this is in fact the repetition code which has extremely high error tolerance thresholds and is a behavior we'd like to replicate in our surface code. Note that even with non-infinite bias and only high bias, we no longer need the vertical direction of our surface code that much because fewer and fewer X errors appear. And so we can use a flattened XZX surface code which uses less physical qubits to encode the logical qubit. So far, it looks like we have the right ingredients. We have a biased erasure model, which seems to produce only Z errors. And we have our XZX surface code, which is extremely good at correcting only Z errors. But if you look closer at what's actually happening during error correction, it's slightly more complicated. So during error correction, we use CZ and control NOT gates. For the CZ gates, as described before, we detect erasures. If an erasure occurs, we replace it in a 1 state, which may or may not introduce a Z error. In practice on the surface code, oh, I'm sorry, just give me a sec. Okay. So in practice on the surface code, at the qubit location where an erasure has occurred, we flag that qubit because we know now that we have put in a fresh qubit, which is kind of uncorrelated with the previous one. And we also flag the stabilizer outcomes that are to its left and right, because we know now that those stabilizer outcomes are likely to be unreliable. And so if, in fact, if we see -1 signs, it is easier for us to pair them together along the qubit that was erased. For the control NOT gate, for neutral atomic qubits, there is no native way to perform a control NOT directly. What we do, in fact, is we perform a control Z gate conjugated by Hadamard's. What this means is that if an erasure occurs and we place the qubit with a fresh atom in 1, the Z error that we originally introduced is converted to X errors on that qubit. So again, we flag that qubit as having an erasure, but we also have to flag the stabilizers above and below it as being unreliable as a result of that X error. And so while X errors do appear, it is still easier to match them together along that vertical direction because we know that that central qubit is unreliable, but we have still destroyed the symmetry that we wanted in the XZX surface code. So in this context, let's examine whether it's still useful for us to have biased erasures as opposed to other structured noise, such as poly errors or unbiased erasures, which arise from any computational state of the qubit. And the way that we're going to do this is we're going to examine an error model where each gate experiences an error with a rate p, where a fraction of these errors are erasures, which we'll separately consider to be biased or unbiased, and the remaining are poly errors. And when we do this, we get the following graph, which I'm going to walk you through. So the x-axis over here is the erasure fraction, where we start out on the left from 0 erasures, so everything is poly errors, and then we move on the right to 100% erasures, which are respectively biased for the orange dots and unbiased for the blue dots. Now the interesting fact is that, okay, we start off with 0% erasures, we see the expected threshold of 1%, but then as we increase the erasure fraction, it turns out that our biased erasures are performing much, much better than the unbiased erasures. In fact, for 100% erasure fraction, we have a threshold of 10% approximately for biased erasures, which is a 10-fold increase in threshold over depolarizing polynoise, and 5% for unbiased erasures. For the neutral atomic qubit, we have to pay attention to the erasure fraction 0.98 because that's the theoretical erasure fraction achievable by these qubits. And even for this erasure fraction, we see a significant improvement in threshold for biased and unbiased erasures, where again, our biased erasure threshold seems to be double that of the unbiased erasure threshold. Now, this may seem surprising because we have already shown that our biased erasures do not preserve the code symmetry. So why do we still see an improvement over unbiased erasures in this error model? The answer lies in more closely examining what is happening during unbiased erasures. If we have an unbiased erasure, our qubit could have started out from any state in the subspace. And therefore, when we replace it with a fresh one in the 1 state, we could be introducing bit flips, phase flips, or a combination of the two. As a result, when we have an unbiased erasure in our surface code, we have to flag that qubit and all 4 stabilizers around it as being unreliable. And we may see a pair of defects, or we may see 4 defects for unbiased erasures, compared to biased erasures where we only see 2 defects in a known direction. As a result, we can say that we lose more information in unbiased erasures, which we refer to as unbiased erasures having greater noise entropy, thus explaining the behavior that we see on this plot, where biased erasures are doing better than unbiased erasures. So that is our analysis of our performance of the XZX surface code with this error model. But the question still arises, is there a way to do better? Because we have shown that our CNOT gates destroy the noise bias and do not preserve the symmetry that we wanted in the XZX surface code. And the answer, somewhat surprisingly, lies in the realm of photonic quantum computing, where entanglement is generated using multi-qubit measurements. Specifically, we are interested in a fusion measurement, which is nothing but a Bell measurement of the XX and ZZ operator on 2 qubits. Now, because these measurements are destructive, we can no longer consider a gate-based approach to syndrome extraction, where we're measuring stabilizers again and again and again. We necessarily have to take a different approach to error correction, which we call measurement-based quantum computation. And now, in this context, I'm going to move on to describing the hybrid fusion protocol for error correction. The error correcting code that I'm going to focus on in this part of my talk is called the XZX Cluster State. On the right, I have shown a unit cell of the XZX Cluster State. The dots in this unit cell represent qubits initialized in the plus state, which we call X-type qubits. The open circles represent qubits initialized in the 0 state, which we call Z-type qubits. The lines between them represent local entanglements. A line between 2 X-type qubits is a control Z gate, and a line between an X and a Z-type qubit is a control knot-like entanglement, where the X-type qubit is the control and the Z-type qubit is the target. How we do error correction on this unit cell is we measure out all the qubits in their respective bases. So we measure X qubits in the X basis and Z qubits in the Z basis. We then collect the measurement outcomes on all base centers of our unit cell and multiply them together to get the unit cell stabilizer product. If no errors have occurred, then this product should be +1. If an anti-commuting error has occurred, then this unit cell stabilizer product becomes -1. In practice, we can create a cluster state of any size by tiling this unit cell across space. Now, this looks like a very complicated entangled state, but a way to simplify looking at this state is to think of it as a foliation or teleportation of the XZX surface code. So we input an XZX surface code state on the left of this cluster state and use this network of qubits to teleport it to the right of the cluster state in a bias preserving way. And that creates our cluster state. It looks like to build a cluster state, we're going to have to use a very large number of qubits that scales with the number of steps of teleportation that we want to perform. But in fact, we do not need this order descaling of qubits. We can use only about 2 layers of qubits of our cluster state and teleport our information of our XZX surface code state back and forth between these 2 layers of qubits, reducing our qubit overhead. Let us now assume that we have built our cluster state. What kind of syndromes do errors in this cluster state produce? Specifically, let's look at Z errors. Z errors anti-commute with the X measurements that surround the vertical faces of this unit cell. As a result, if we have Z errors, then we have pairs of syndromes or defects pairing horizontally from left to right across our cluster state or going into the horizontal plane of our cluster state. There is no Z error in our cluster state, which will create a vertical pairing of defects across horizontal planes. As a result, when we're trying to do error correction, we can consider each horizontal plane separately while pairing or matching these defects, and again have a reduced dimensionality of our matching problem, which is called asymmetry, leading to higher thresholds. So this tells us that if we already have a cluster state that experiences Z errors, it has high thresholds. But the problem remains, how do we construct this cluster state without destroying the noise bias or using CNOT entangling gates? And our protocol to do so is as follows. We will first generate small entangled states that we call research states. We will then stitch them together using control Z gates and fusions, with the idea that both of these processes are bias preserving and only introduce Z errors, if any errors occur, to the cluster state, which then retains this 2D system symmetry, leading to higher thresholds. I've already described how control Z gates are bias preserving, but let's take a closer look at how fusions manifest in this platform. Here on the left, I've shown the tailored fusion circuit. We entangle an ancilla qubit with 2 data qubits using control Z gates followed by erasure detection. If no erasure is detected, we measure out all the qubits in the X basis. And ancilla measurement gives us the ZZ measurement outcome, and we can recover the XX product that we want from multiplying the individual data qubit measurements. If an erasure does occur, however, we do something slightly different. We switch our measurement basis on the data qubits to Z to get the ZZ product. As a result, what happens is that in all cases, erasure or no erasure, we always recover the ZZ measurement outcome with 100% guarantee if there are only erasures. But if a biased erasure occurs, then we lose the XX measurement information. And over the next few minutes, I'll show how this is equivalent to only creating Z errors in our cluster state. But before that, I'm just going to take a step back and talk about how we generate these small entangled states that we call resource states. The resource state we are interested in our protocol is an 8-body entangled state that we call the 8 ring that consists of 8 qubits entangled with a series of control NOT gates. We use the following circuit to create our 8-ring state, which consists of a series of control Z gates followed by Haldemann's and erasure detection. It looks like this circuit can potentially introduce X errors, but there's a subtlety to our protocol that ensures that this is not the case. If no erasures are detected, we say that we have succeeded in generating our resource state, and we pass it on to the next step of our protocol. If, however, an erasure is detected, instead of replacing that atom in the one state and running the risk of having it introduce X errors, we simply reset the qubits and try again until we have successfully generated our 8-ring resource states. This ensures that we have generated control NOT-like entanglement without introducing X errors. Let us now place 2 of these resource states next to each other and fuse the Z-type qubits, which are adjacent and highlighted in gray. For simplicity, I'm only going to show those 2 Z-type qubits and their immediately neighboring X-type qubits. And also, for now, just focus on the XX part of the fusion measurement, which is both XX and ZZ. When we perform only the XX measurement on these 2 qubits, 2 things happen. Firstly, we pass on poly Z corrections to 2 X-type neighbors that are dependent on the measurement outcomes. So if we have a 0 measurement outcome, we apply identity to those neighbors. If we have a 1 measurement outcome, we apply Z to those neighbors. Secondly, this XX measurement outcome combines these 2 Z-type qubits into a single virtual Z-type qubit, which is still secretly 2 qubits with the logical operator shown. This will come into play later. The important thing to focus on is that if this XX measurement is a part of a fusion and a biased erasure occurs, we lose the XX measurement outcome, which manifests as a lack of knowledge of whether to apply identity or Z to these neighboring X-type qubits, which looks like a Z error on our cluster state. This is promising, and we're going to use it in our protocol, the hybrid fusion construction. So we start off by placing an array of 8-ring states in a single 2D plane with 1 8-ring highlighted in green for clarity. And we perform our XX measurements between neighboring Z-type qubits, which combines all of these 8 rings into a single 2D planar array. As before, if we have a lack of information about the XX measurement outcome, that creates correlated Z errors in our cluster state. We then place many of these arrays on top of each other with consecutive planes displaced by half a unit and apply control Z gates between X-type qubits across planes, creating our final cluster state, which teleports an XZX surface code from left to right. The final step of our protocol is to measure the qubits in their respective bases. This is simple enough for X-type qubits, but if you remember, our Z-type qubits were secretly 2 Z qubits with a 2-body ZZ measurement. When we measure this 2-body ZZ operator and combine it with the XX measurement we did at the beginning, we get a complete fusion. Now, this seems somewhat counterintuitive because it looks like that for our fusion operation, we have to perform the XX part of the measurement at the beginning and the ZZ part at the end of our protocol. But in fact, this ZZ measurement commutes with all other operations we're using to build our cluster state. And so we can pull it to the beginning of our protocol at the same time as our XX measurement and do a complete fusion all at once. So to summarize what we're going to do in practice, we generate our 8-ring resource states and post-select on the absence of erasures, ensuring no X errors are introduced. We then stack these 8 rings into layers and fuse the neighboring Z-type qubits, which again ensures that biased erasures at max produce correlated Z errors. We then apply control Z gates between X-type qubits across layers and measure out the X qubits in the X basis because the Z qubits have already been measured as a result of our fusion. What this protocol does is ensure we have created our cluster state in a symmetry preserving manner, where any biased erasures during the construction process only manifest as Z errors in our cluster state. There's also one small subtlety to note here is that while preserving symmetry, we have used an increased gate count. To create CNOT-like entanglement, instead of using a single CNOT gate, we have used 2 control Z gates. And there's also an element of post-selection happening during the resource state generation that slightly increases our gate count. So with this benefits and those slight disadvantages, let's examine how our construction performs. Like before, we're going to use the same error model, where each gate experiences an error with a probability P, where a fraction of these, called the erasure fraction RE, are biased erasures, and the rest are poly errors. As we know before, the threshold error rate when we have only poly errors is about 1%, and the theoretical achievable erasure fraction for the neutral atom ytterbium qubit is 0.98. And when we use the XZX surface code approach, we showed that this threshold increases to 8.2%. Let's examine our hybrid fusion approach. The threshold in our hybrid fusion approach increases to about 10.2%, which is a 20% increase approximately over our circuit-based approach, and is thus further relaxing our gate infidelities. But more interestingly, we have the fact that our symmetry is preserved, which means we don't need this vertical dimension of our cluster state so much anymore because we are getting primarily errors in the Z horizontal directions. And therefore, we can use rectangular cluster states with fewer qubits. Additionally, because we are using a measurement-based protocol, our qubits only ever experience shallow circuit before they are measured out. And we don't need our atom replacement mid-circuit anymore because our qubits are measured out after these few gates applied to them. So this further relaxes the experimental requirements in order to build our error-correcting code. Another interesting fact to note is that our neutral atom is limited in that it can only achieve a maximal erasure fraction of 0.98. If someone were to find a hypothetical qubit that experienced 100% biased erasures and no poly errors, the gate level error threshold could in fact increase to about 18%, which would be very nice. So that brings me to the end of the constructive part of my talk. We have introduced this new form of structured noise, which is biased erasures, and is in fact the dominant noise in this metastable ytterbium qubit. We have also shown that this biased erasure noise is extremely easy to correct compared to other structured noise that has been studied thus far in discrete variable qubits, leading to higher thresholds for our gate-based approaches. And by looking more closely at our qubits and its capabilities, we have designed a measurement-based protocol that uses carefully tailored resource states and fusion protocols in order to reduce qubit overhead and relax hardware requirements and further increase the threshold. Current and ongoing work includes achieving this 98% erasure fraction in practice. Currently, a recent work by Jeff Thompson's lab has achieved a 33% erasure conversion. It also involves investigating whether biased erasures are the natural noise in other qubit platforms and can be exploited over there. And lastly, an interesting result of our work is that by using the measurement-based approach, we have circumvented the requirement of bias-preserving CNOTs in our error correction protocol. And this same concept can be extended to further error correction protocols and examined there. With that, I'd like to thank my collaborators once again and welcome any questions. Here you go. That's working.
Thanks for the nice talk. I have two questions. First is, it seems like errors being biased is true even for the Pauli error case, because you only have errors when the state starts at one state. So could you exploit that? And the second is like, why is experimental rates only 33% while it's a pretty big gap? So right. I was wondering.
So just give me a sec. So that I'll answer the second question first. So getting a good erasure fraction depends on being able to detect, sorry, can you hear me? So getting this good erasure fraction depends on you being able to detect this entire set of external sets, this entire set of external states E. This is a little bit difficult to do in practice. And what has been done so far in the Jeff Thompson lab is that they have put kind of these fluorescence detectors at a subset of these external set of states E. So not detecting all of the decays or all of the exits from the computational subspace. But you can engineer some more complex detection pulses and then increase your erasure fraction. And could you repeat your first question? I'm not sure I understood.
So the biased erasure occurs because you basically have errors only when you have errors qubit is in the one state, right? Mm-hmm. And yeah, so if it becomes erasures, it's biased. But also for the Pauli error part where it goes back to the qubit subspace, mm-hmm. could we use that same property that error occurs only when it's one state and improve the threshold?
So the Pauli error case is a bit more complicated. What happens, you can look at this slide itself. During a during a 2-qubit gate, you excite to the Rydberg level, and then you decay back to the computational subspace. So you're not able to tell anything has happened at all by looking at the qubit itself. You can only look at the syndromes, and those syndromes could be Z errors, the syndromes could be X errors. So in practice, you don't really have a biased Pauli noise model during this process. Does that answer your question?
Thank you, yes.
Yeah, thanks for the nice talk. I'm curious about the experimental question. So like you mentioned the post-selection part, I assume the theory assumes that it is not going to limit like the generation of the entangled state. So I'm just curious, does that actually impose any limitation in terms of like if one actually want to build this experiment?
So I'm a theorist. I don't have the best answer to this question, but this is something that we briefly thought about, because in theory, what you could do is that you could generate your entire cluster state with post-selection, but that involves generating this big resource state, which involves a lot of gates and is not the most experimentally feasible thing. So there's probably a good balance of the size of resource state that you want to post-select on and the efficiency with which you can perform this protocol. And that's like future/ongoing work that we're doing. But we won't have an answer for that right now.
Thanks.
Yeah, so follow up this great question. The threshold you use as a metric of success of achieving better code design might not be sufficient, right, to describe this type of cost, space-time overhead in the measurement-based code. So is there a different metric you think we can use to compare between different measurement-based code?
So what we are looking at is the sub-threshold scaling, because in practice, your gate infidelities are rarely 8% or 5%. They're probably on the order of 2 or 3 nines. But because we have a combination of erasures and Pauli errors in our error model, the sub-threshold scaling is a bit complicated. And therefore, we're currently working on how to get this kind of characterize this behavior below threshold in an efficient or analytically correct manner. So we don't have an answer to that yet.
Cool. Yeah, very exciting work. Is there any other question? If not, let's thank the speaker.